All right, so I'm recording this as ideas for some of you to decide whether you want to use it or not, so that you can kind of practice a little bit and gain a better understanding of the processor architecture. So this is a pretty typical processor architecture. So one thing you can potentially do is in order to kind of experiment, okay, is to um, disconnect some of the wires or some of the tunnels from the ROM. So let's just say that you want to experiment with ADDR mux. Okay, so ADDR mux is this particular signal. So what you can do is to take it out. Okay, so so what I'll do is I'm gonna do Control A, Control C. So I'm copying and pasting to a new circuit. All right, so paste over here, and we don't have the necessary library to do it. Okay, fine. Let's close that. Discard. All right, so within the same processor 0003 file, in addition to main, you can make a new circuit. So I'm going to add a new circuit here, and we'll just call it experimental. All right, so click OK, and now I do a paste. So because it is in the same file, so all the references to external library are still okay. So you don't have to re-specify, where to get reg bank, the register bank, and where to get the ALU again. So once you get here, okay, you have a lot of options. Okay, one potential option is to make your own opcode. Okay, now that sounds like, wow, that's a lot of work. It's not really as much work as you think it is. So the first thing you want to do is to find empty slots for new opcodes. So we go to edit content in the ROM, and what we'll do is we are trying to find locations where the address is ending with a 0. The least significant hexadecimal digit is a 0. So we know that 000 is corresponding to no op, but that's also how we do the fetch cycle. So you don't want to mess around with 000. 010 is the halt instruction, so you don't want to mess with that either. But you can see there's a whole bunch of available opcodes, so that you can, if you want to, you can play with those. So let's just pick 020. Okay, this looks like it's a vacant slot. No opcode currently is using 02 as an opcode. No instruction, I should say, is using 02 as an opcode. So we can actually use that. Okay, and let's just say that you want to experiment with something that's based on LD. Okay, so what you do then is to go to the opcode table, and you find out what is LD. What is the actual opcode of the original LD, which is here. And LD has 16 variations, so you have to kind of pick one of the 16 variations. So let's just say that we want to play with using B as register X and using C as register Y. Okay, so that would be 01 for XX and 10 for YY. So it becomes 0110 or 6, for the least significant digit in base 16. So this whole thing becomes 76. Now, why do we want to know 76 in this case? So what we do now is we go to location 760, which is right here. So this is the content. This is the value in ROM to specify all 26 bits in order to perform load B from where C is pointing to. So we copy it. Hopefully Control C works, and then go back to the location where we want to. Control paste. Control C, copy and paste doesn't work. So you kind of have to either type in the whole thing, or you can kind of do the ROM file thing. But the idea is to replicate that number at this location. And then what you can do is to change that location according to the bits that you want to change. Now that gets a little bit hairy. Okay, it gets a little bit hairy because then you have to find out which bit you want to modify. Um, so what? Let's just say that we are dealing with address mux, ADDR mux. So what you need to do is to click on the wire. Okay, make sure that you're using the poking tool. Click on the wire of the thing that you want to experiment with. Okay, and it will highlight all the nodes, including the one that is going into the splitter. But because this particular splitter, the merged end of this particular splitter, which is Ucode data, is coming out of another splitter over here, so that really kind of gets a little bit more difficult to find out which bit we are talking about. Um, but I can show you how you can actually figure it out. If this method will work if you just want to kind of play with 1 or 2 bits, but if you want to play with a whole bunch of bits at the same time, this method can get kind of rather tedious. So right here we can see that address mux is connected to bit 16 is the number on top of the wire of the split end that indicates the bit number. And everything within this particular splitter is offset by 3, because bit 3 coming out of this wire becomes bit 0 on this particular wire. So that means anything that is like you have to add 3 basically. If it's bit 16 after the split, then it is bit what 6 plus 9 is 9, so it's bit 19 from here. So now you have to look into how to change bit 19 within a 6-digit hexadecimal number. You probably want to use a tool to help you do bitwise operations, especially shifts and also bitwise and bitwise OR. So that way you can actually kind of reassemble the entire bit pattern into a hexadecimal number. A spreadsheet can be very useful for that, and I believe that I might still have a spreadsheet in one of the folders that is already shared with you guys. So let me check out the processor folder. And one thing I want to do is, okay, I took that out already, which is good. Okay, so there's a spreadsheet called Microcode worksheet. Okay, so that's something that you might find useful. So what it is each column is corresponding to a particular bit out of ROM, and row 2 is already indicating the bit number within the 26 bits, so you don't have to enter any of this. And then what you can do, or what you can do in this case, is really just to specify you want microcode pointer reset to be a 1 or a 0. That's basically bit 25, which does not have its own tunnel. This is microcode pointer select, which controls how the microcode pointer updates, which also does not have a tunnel. But we can see familiar names like PC enable, PC mux mux, address mux is right here. So you can now change this. And then this is a pretty wide spreadsheet, and it's poorly formatted, but it's okay because at the very end we get a hexadecimal representation of all the bits, okay, added together. So we can check this out, okay. So we can quickly find out whether a particular bit pattern is correct or not. So this one here is supposed to be CPR. It's CPR AB, and okay, so CPR AB, and this is okay. This is the value for that particular bit, and this is that bit shifted by this amount. Okay, so we want to look at the second row. So we want to look at row 15 in this case to find out what is the ROM content. So the ROM content for CPR AB is supposed to be 1500990 according to the spreadsheet. So now we can go to the okay, I'm being super lazy. Instead of using the opcode table, well, let's do it using the opcode table. I changed my mind again. So look up CPR AB, and CPR is right here. So if I'm using CPR AB, it is going to be a 5 on this side, and AB is 00 for A and then 01 for B, so it's 51 in terms of the opcode. Then we go to the Logisim, and then we look up the ROM content, and then we go to 510, Okay, so we go to 510, which is right here, and it gives us a value of 1500990. And I obviously have forgotten entirely what the other spreadsheet is telling us. Oh, okay, it is correct. Okay, it's the same. It's 1500990. So this particular, obviously you have to kind of make a copy of this spreadsheet first in order to make changes to it, because right now it is my spreadsheet. So if you want to create your own spreadsheet, you have to change it. And this one here, okay, I'm just giving you some more examples. Row 16 is corresponding to LDA, comma B, and B is in parentheses. So then row 17 will give us the actual hexadecimal code for that particular opcode. So it is 1501016. Then we go back to the opcode table to find out what LDAB is supposed to look like. This is supposed to be 71. Then we go back to here, look up 71. There we go, 710. It is 1501016, which may not be identical to what I have in the other spreadsheet. Nope, it is identical. Okay, so because I cannot remember numbers, digits, when there's no specific pattern to it. Well, I mean, there's a specific pattern to this one, but it's still pretty difficult to memorize. So this spreadsheet is potentially a great tool so that you can kind of experiment. So once you have identified a particular hexadecimal digit like this, let me see if I can Control C and then paste it into a location in ROM. So remember, don't overwrite these things, okay? And it's probably a better idea if you just kind of make a copy of your processor file first. The ROM content is stored within the processor file. So if you change the ROM content, it is saved along with the processor file. So I'm doing Control V to see if it would paste. Control C, nope, it does not paste. So what you need to do is really just kind of put it side by side so it's easy to copy. So now it's 1501016, which is identical to LDAB, which is not a whole lot of fun. So what you can now do is to say, I wonder if I change ALUOP, whether that will impact the result of this operation. So you go to ALUOP, which is column H, and right now it is specifying operation 0. So if you want to, you can say, I want to try operation 3. Okay, now the next row is going to change the value, because this is what I'm selecting right now. That particular cell is 3 and then left shifted 16 times. Okay, so now I go back to the long hexadecimal digit, which is over here. So you can see how the 3 is now appearing right here. There was a 0 here instead of a 3. So now I can copy that over here and say 153, what was it again? 1016. Okay, and I click close window. So now I have to inject certain things into the processor to test this new operation. So it would be a good idea to put something into register B, for instance. So I go to the processor, I go to reg bank, go to processor B, and say, I wonder which location I want to change. Let's make it 7B. Okay, so this is the pointer. I'm going to location 7B and retrieve that content in RAM into register A. So now we go to RAM, okay, and then we go to that location, right click.
Hi there, Tack. How are you doing?
Just hold on a second here. I'm recording. Hi, Randy. I'm in a part of a recording, so I'll be right back in about 5 minutes.
No problem.
Okay, thanks. All right. So now we go to the location, which is 7B. So 7B this is 789A, and this is 7B. So we'll change that content to, let's say, F2. So these values are completely random. Okay, I'm just testing it. So now we close the RAM content editor. And now we need to test the new opcode. So you might say, well, but that opcode is not, the assembler does not recognize anything to generate that opcode in a RAM file. That is entirely correct. but that's okay. We don't need that because what we are going to do is we are just injecting that code into the microcode pointer. Okay, now when you do something like this, you have to be super careful because you have to take the program counter into consideration. Now, this opcode does not do anything with what the program counter is pointing to, so it's okay. But if you're dealing with something like LDI or JMPI, anything that ends with an I, um, it does rely on the current value of the program counter. So for those, if you want to experiment with those particular instructions, then you have to be, a little bit more careful. Now, the other way you can do this, without having to worry about what else you have in RAM, is really just go to the first location in RAM and put in the opcode that we just quote unquote hijacked. Okay, so it's opcode 02 in this case. So now instead of using the assembler to generate the opcode 02, I am just forcing the content into RAM. So now when I Control T, do all the transitions, we'll go to that location to execute, and the program counter would have been correct as well. So if I am using this method to experiment with an instruction that uses an immediate constant, it would still be, it would work correctly. So I'm going to do a Control T 4 times. 1, 2, 3, 4. So now we are at location 020, which is not, it doesn't have what I want it to be. Okay, so maybe I did not change the right location, or it didn't stick. Yeah, I guess it didn't stick. Okay, let me try that one more time. Then I have to go because I have another meeting that has already started. So let me do this one more time. 153 1016, and this time I press the enter key. Okay, so maybe that makes a difference. There's no need to save it. When you save, it is just saving the ROM content into its own file. So there should not be a need to save it. So I close window, go back to Logisim over here. Aha! So this time it does work. So let's check out the whole thing here. So RAM is selected, it is in read mode. The address port is being driven by input 0, which then goes into which is output 0 of this demultiplexer, and then inside the register bank we are indeed using register B to specify output 1. So everything seems to be correct 100%. So far, but the content is trying to update it with is incorrect. It's using register B is has a content of 00. I thought I changed it to something else, but anyway, but I think this gives you a general idea of how to experiment. I think I confused myself because I was using one for the first operation. I'm using the other one for the second
Hi there,
operation.
Veronica. How are you?
I'm
So I
good.
gotta
How
go
are
to
you
the
guys
other meeting.
feeling?
I'm gonna
We're
upload this
doing pretty
video
good.
so
Tack
that you
is
guys
doing a
can
recording right now, so he'll be with
play
us
with
in a
this.
few minutes.
All right.
Oh,
So
okay.
I'm
Sorry
gonna
I missed
close
today's
the
meeting.
recording now.
Um,
Yeah, that was no problem at all.
yeah. So